talk so easily. So, later when we start talking about, we're gonna get into here, like, this is alpha, this carbon that this hydrogen is on is alpha to the carbonyl. So when we start getting into alpha carbonyl chemistry, this guy and this guy, you'll notice that, like, we start doing chemistry with that. But if we've got a carboxylic acid, this guy wants to act as an acid more than this guy does, right? So if you've got this on here, this will do something first. Yeah? It's kind of a how reactive can we do stuff, right? So, because a lot of the chemistry later with carbonyls, we end up, we start by either deprotonating or we're going to end up deprotonating after something else. Okay. So this is the reference sheet that I'm going to give you guys during your exam. If there's anything else that feels useful, let me know. Last year people requested in chapter 15, they've got the tables of in chapter 16, they've got the tables of like boiling points or like molecular weight and boiling point or something. I don't want to give you guys those because those are just, you don't have to memorize that table. It's more like I want you to be able to recognize the pattern, right? If you've got a higher molecular weight and all the same functional group, higher boiling point. If you've got a functional group that is polar, higher boiling point than the nonpolar, but lower boiling point if it can't hydrogen bond. Yeah? So those are the things I want you to know for that. But if there's something else like this that seems useful to you guys, let me know. Okay. All right, we're good. I think we will get to, honestly, right where I suspected we might get. Granted, I guess that wasn't a really ambitious suspicion, but okay. So, we talked about anions of terminal alkynes and how this is a thing you can do, right? You can attack a carbonyl and get this and then protonate it. And then you've got this triple bond, which is great for doing additional chemistry. So then you can turn that into a ketone or an aldehyde. Here's how you do that. And then you could attack it with another thing. Not a Grignard reagent or an organolithium compound, right? Because those are way too aggressive and they're just gonna use this and go be useless. Turn into the really cheap thing that you could have bought from Sigma when you bought the really expensive thing. But you can use other ones to do stuff with this. So these are the kind of things that I want you to be thinking about multi-step syntheses. Like think about these kinds of things with respect to multi-step syntheses in case you need to do a, like how would I get to this in 2 steps from here? Oh, I'm gonna have to do several different things to it, or do a retrosynthetic analysis of this or something. Yeah? Okay, addition of HCN, cyanohydrin. Let's see, we are going to add cyanic acid. Right, that's not cyan. Yeah, no, cyanide is the ion. So we're gonna add cyanic acid to the carbonyl group of an aldehyde or ketone to give a cyanohydrin. A cyanohydrin is basically just, it's got a CN group and it's got an alcohol group. I call it a CN group right now because we're calling it a cyanohydrin, and well, it's a group that comes from cyanide that looks like cyanide, and it's a hydroxide, so hydrin, but when it looks like this, we call this a nitrile, right? Yeah, CN3, or CN with a triple bond there, that is nitrile. So, I mean, do this. Basically, the concentration of the cyanide ion, because are we actually going to be attacking this carbon with cyanic acid? I mean, I don't know, we could try, but honestly, what's going to make this a much better nucleophile if we deprotonate it, right? So if we deprotonate that, then we've got a bunch of cyanide ion, and then that's a much better nucleophile, and we'll have more of it to attack. So, and HCN is a weak acid, right? So not a lot of it dissociates. So we've got a little bit of cyanide in there. What we can do is we can either bring our own cyanide, dissolve NaCN or KCN in water. That just brings our own cyanide. That's sort of, I mean, basically you're just adding the nucleophile that you want, but when it comes down to it, because we actually end up protonating this, so we actually do kind of use this hydrogen, really what we're doing is, whether you just add NaCN or KCN, or you just drip a bunch of NaOH in there or something, you're adjusting the pH so that way more of your cyanic acid is actually cyanide and not cyanic acid, right? And this one calls for mechanism. So, I'm going to leave this slide up as the next slide just sort of says the mechanism time. Why is this room the way that it is? Numbers on my notes this time, which is useful, but the notes like split up by chapter, so the page numbers just start over again. So I think I need to learn how to print page numbers like 16-point page number or something like that. All right. Formation of a cyanohydrin. We're going to do, fine, I will write it the way that they have it, even though I hate it. Why did they? No. They went a step too far by drawing out the carbon in the middle, and it's just way too ugly. Is it actually, let me do this. Okay. Is one of these actually more helpful, like, to see while I'm drawing these out than this is? Because if it is, I will absolutely do that. Like, if it's more helpful for some of you, I will. Yes.
I would say only because the central C is what's getting attacked, that it might be easier to draw the C to give you more space for the arrows.
That's a good idea. Okay, I can do that. Yeah. I'm not going to start doing that all the time, but part of that is because ChemDraw takes a lot of time, and then to make ChemDraw show the carbon,
Oh, I thought you just meant on the board.
No, yeah, but like for your exams,
Yeah.
like I want to get you used to both, but also this is why I suggest it's not a bad idea to bring an extra color or two to mark things in exams, because it really makes things easier to see how many carbons there are. Okay, so this, or can we do that? Okay, cool. I just have this, I don't know. Seeing a CH3 at the end of a line just like brings me emotional pain, because biochemists love to do that. And it means the same thing if you put nothing on the line. Exactly the same thing, and it looks so much prettier. Like I can get that carbon in the middle. That's the carbon that's doing stuff. So yeah, that makes sense. But those guys, chemists are inherently lazy. That's our lesson for today. All right, so we started with HCN, but really we have this because, oh. If I push this over to here, can everyone still see it all right? Okay. Trying to get as close to that as possible, but because I'm writing this way to that way, I'm either gonna stand directly in front of this, or I'm gonna be further from that. Hopefully that still picks me up. If it doesn't, somebody let me know if this is like too far, and I'll try to stand over there and reach across. All right, so we've got this. Let's find our electrophile and our nucleophile. And then get marker all over myself. I need to take like an isopropyl bath, shower after every lecture, or at least just wash up to my arms. Okay, so nucleophile attacks electrophile, right? When in doubt, find a nucleophile, find an electrophile, draw an attack arrow. And then, for the rest of the majority of the points, figure out what to do to not have 5 bonds go into that. If it's a leaving group, or if it's usually gonna be this, because honestly, half or slightly over half, maybe a solid. Because honestly, chapter 19 is also this, and I think, yeah, I'm pretty sure our exam 1, I was not planning on including chapter 19. So like a good more than half of organic 2 is a bunch of carbonyls and what they do. So usually it's this. When in doubt, find an electrophile, find a nucleophile, draw an attack arrow, fix the 5 bonds that you just made towards something, and that will get you many partial credit. Even if it's the wrong thing, if you find something that is could be reasonably considered an electrophile, and something that could reasonably be considered a nucleophile, and you draw me an attack arrow from the nucleophile to the electrophile, that's some amount of points. Even if it's the wrong things, you have an idea of nucleophiles, electrophiles, you have an idea of how to attack. That's partial credit. Okay. So we do that, and we get reversibly too many colors. That with that. Yeah. Yeah. And that I didn't draw at an angle like on purpose. I mean, I'm not gonna be nitpicky with you guys when you're drawing things, since there's a lot to think about, especially with mechanisms. But I drew that straight, or as a nice little line, because this actually is linear, right? Because we've got a triple bond and a single bond, nothing else is bonded to that carbon, so the best way to get those things as far apart from each other as possible is to put them in a straight line. Okay. This is the last. Yeah, okay. So we get this, and then we go, wait a minute, I see a negative charge. Let's do a real quick check and go, are we in an acidic or basic environment? Which one are we? So we added cyanic acid, right? But then to actually make this reaction go, what did we have to take the pH to? We had to add a bunch of base, right? So weirdly enough, yes, we added cyanic acid to this, but we had to make the reaction basic to make it go because this is not a strong enough nucleophile. This is a strong enough nucleophile, and it's a weak acid, so when there's this around, there's mostly this and there's not a lot of this. So actually we're in a basic environment, right? Are we good on this step, or do we need to do another step before this? Basic environment, negative charge. Okay, not okay. Okay, yeah? Basic environment, negative charge, we know we can associate that because OH minus, that's basic. So we're good on this step. Yeah. And then we can go, hey, you know what? Even if it's a really basic solution, I bet there's some of this floating around. Actually, you know what? I take it back. When I said we could add sodium hydroxide, oh, it's in water, so I guess we could. Yeah, all right. We could, but if you add a bunch more cyanide anion, you're gonna have more of that, so sure, we're gonna do that. Because this can happen in water, weirdly enough. Okay, so then to complete this reaction, this guy's gonna go, hey, how about I take, that is an arrow specifically at the hydrogen, not the bond. How about I protonate myself, like so, and I guess this is also reversible, isn't it? Yep. Fine. Reversible. And we're going to get so many colors. Okay. Which is the same as that. Same. Yeah. And, okay, 2 minutes of class left. So we can talk about this a little bit at the beginning of class tomorrow. Wait, today's Thursday, tomorrow. But just to kind of start with why we care about this, so cyanohydrins are really useful as synthetic intermediates. You can do a whole lot of chemistry once you get to this point, right? Because we've got an alcohol that we could do something with, right? We've got a triple bond. Those are great to react with things. Those are very reactive. It's a nitrile, not just a carbon-carbon triple bond, so we can do stuff with it. Let's see. Nitrile is reduced to a primary amine. Okay, yeah. So if you do, you know the nice way that we get rid of double bonds, right? Can you use nickel and hydrogen gas to get rid of, to hydrogenate double bond, carbon-carbon double bonds in, okay, I always think of platinum, and so I couldn't remember if nickel would do it, but you can use nickel and H2 gas to get rid of all of that, hydrogenate that like a hydrogenated oil, and except not, and you can make that into a nice little primary amine. If you use an acid catalyst, you can actually get rid of this and one of these hydrogens, and you can do an acid catalyzed dehydration, not dehydrogenation because that's hydrogen, but dehydration because that's water. You can get rid of the water right in there and turn that into a double bond. And now you've got a double bond and a triple bond, and the world is your oyster. So these are things you can do. That's why it's useful to be able to do this. You guys have recitation after this. Class is over. I've kept you a minute late, so and you guys are going to be in here. So yeah, go be free or take a break before recitation, or come